on to the second part of this chapter, and we're first going to look at the gradient function. So we've got here two exponential functions, 2 to the power of x and 3 to the power of x. Very similar, except this one is a bit steeper here. So the gradient of the tangent at every point, if we were to plot that, would look something like this for 2 to the x. So the gradient, remember, changing y over changing x. And for 3 to the power of x, it would look something like this. So very close to each of the original graphs, following a very similar shape. In fact, both of them are a multiple of the original graph. This one is actually 0.693 times 2 to the x, and this one is 1.099 times 3 to the x. So if 2 to the x, the gradient function, is below 2 to the x, and if 3 to the x, the gradient is above 3 to the x, there must be a base somewhere between 2 and 3 where the gradient function actually matches perfectly onto the original function. And there is. And that value is 2.71828. And that's called the exponential function. So e is another example of a rational number. It's like pi, its decimal never repeats, it never ends. It cannot be expressed as a fraction. So this is a very, very special number. And it has the fantastic property that if you've got the original graph e to the x again, is somewhere between these two graphs, then the gradient, when we differentiate it, you get exactly the same thing. Now we can extend that forward. If you have y equals e to say kx, then when we differentiate it to the gradient function, it's simply k times e to the kx. Okay. So for example, if you had y equals e to the 2x, then dy dx would be multiply 2e to the 2x. Okay, on to example 3. This asks us to differentiate a e to the 4x. So e to the 4x differentiates to, just drop the 4 in front, 4 e to the 4x. b, e to the minus half x, just simply drop the minus half in front, that differentiates to minus half e to the minus half x. And c, 3e to the 2x, if we drop the 3 in front, do 3 times 2 is 6, differentiates to 6e to the 2x. So the power all stays the same, and whatever the coefficient of the power is, you just multiply, if there is a coefficient there, by that value. Okay, example 4. We have to sketch some graphs, so we need to sketch the graph of e to the 2x firstly. So with e to the 2x, I'm going to start off with my base graph of e to the x, because I know what that looks like. It's just a curve that goes up and up and up and up and up. So if I want e to the 2x, I simply change the x to 2x. So that's going to be a horizontal squash. Remember in the cage, all about horizontal, and you're squashed if you're a lion. So it's going to be a squash by a factor of 2. So in terms of what the graph looks like, well, it looks very, very similar. So it's the original graph that's been squashed by a factor of 2. B needs this time sketch the graph of 10e to the minus x. So I could use that as my base graph, but I'm going to stick with e to the 2x. So we're going to need to swap x for minus x, and we're going to need to multiply it by 10. So here I should have written f of x equals e to the x. And this is the graph that I want to draw. So I need to swap the input value to minus x and multiply by 10. So this is going to be a horizontal reflection, and this is going to be a stretch vertically by a factor of 10. So I need to take the original graph, which looks similar to this, except it's e to the 2x. I need to flip it and then stretch by a factor of 10. So that will look something like this. So flipped, and when we stretch by a factor of 10, the 1 becomes a 10. I mean, you can check that by substituting in 0 into the graph. So 10 e to the minus 0, e to the minus 0 is 1, times 10 is 10. So we know that point is correct. And C, y equals 3 plus 4e to the half x. This is quite a complicated one. So if I start off with my base graph of e to the x, then if I look firstly, the power changes from x to a half x. So now it's going to be f of a half x. The input value changes from x to a half x. And that'll give me e to the half x. I then need to multiply by 4. And then I need to add 3. Okay, so in terms of the transformations, I'm going to need to squash by a factor of half, which effectively is the same as a stretch by a factor of 2 horizontally. I'm going to need to stretch it by a factor of 4 vertically, and then I'm going to need to go 3 up. Now here we've got 2 vertical transformations, and the order does matter, because if you move 3 up, then stretch by a factor of 4, you'll get a very, very different graph. Now with vertical transformations, the order is intuitive, so it's the order you'd expect. So you do whatever's closest to the x first. So stretch by a factor of 4, then go 3 up. And also there's a very easy way to tell. You can tell where it goes through the y-axis. So when we put x equals 0 in, we get 4 e to the 0 plus 3. E to the 0 is 1, so 4 plus 3 is 7. So we know it should be going through the y-axis at 7. So e to the x graph, we've got to stretch by a factor of 2. It doesn't really do a great deal. Then stretch by a factor of 4 vertically. Okay, and that doesn't actually do a great deal to the shape, except it's going to go from going through 1 on the y-axis to 4 on the y-axis, and then 3 up. Well, we'll do this bit first, and then go 3 up. That's going to look something like that. So we've just stretched it by a factor of 2 that way, stretched it by a factor of 4 that way. Its shape is very, very similar. But now we need to shift all of it 3 up. What happens is the asymptote, which was the x-axis, is going to go 3 up. And to show that on a graph, we do a dotted line. So it's going to have an asymptote at y equals 3. So it never quite reach that. And 4 plus 3 is 7. So y equals 3 plus 4 e to the half x. Okay, and that is all the examples on the second part of this chapter. So if you can now have a go at exercise 14b, which is on page 316.